Okay, well, I would like to thank the organizers for inviting me and for extending the hospitality to all of us, and also separately for scheduling my talk in the afternoon so that it's only 6 a.m. at CERN, unlike for some other less fortunate speakers. So I would like to start. It's not working well. I would like to start with a little bit of history and to remember the 70s and the 60s when quantum field theory was thought to be in trouble because it couldn't describe, seemingly couldn't describe, the observed phenomena in the world of hadrons. So we know very well that this one idea which tried to tackle it was the S matrix, and which gave rise to string theory. But another idea, which was also popular a little bit later in the 70s, so that was the idea that perhaps we shouldn't abandon field theory. We should just think that strong interactions at high energies is still a field theory, but of an unusual then type. So in modern language, what these people thought, they were imagining a strongly interacting fixed point at high energies. And this idea was championed by, most prominently, by two groups. So in Italy, it was championed by a group of a Florence professor, Raul Gatto, and his younger collaborators, Sergio Ferrara and Aurelio Grillo. For Sergio, I even found a young picture. And in the Soviet Union, it was Alexander Polyakov. And by the way, Raul Gatto was also a grandfather of string theory because he was the advisor of Gabriele Veneziano. And so these people, they, in a series of papers, in a series of about a dozen papers written in 71 to 74, they basically laid down the foundations of modern conformal field theory. And so what did these people understand? They basically understood everything. So these are the things that date to those early days. So they understood the classification of primary operators. Well, this was actually done a bit earlier by Mak and Salam. They understood the unitarity bounds on the dimensions of the operators. They understood the conformal invariant OPE. And they also discussed the constraints of conformal symmetry on the correlation functions of primary operators. So all those things that we now use. So it's amazing in retrospect how modern the papers of these two groups of people were. So they still serve a valuable resource in the study of CFTs, unlike some other approaches which had conformal symmetry in the title from those days, which in retrospect are completely outdated. For example, the approach of skeleton expansion. And so most importantly, what these people realized is that they defined a conformal field theory as a set of correlation functions, so of local operators. And those local operators form an algebra, an associative and commutative algebra. And so any conformal field theory is characterized. So they identified this set of numbers which characterize any conformal field theory. So these are the conformal data, what we call now the operator dimensions and the OPE coefficients. And they also realized that OPE associativity provides a strong constraint on the set of numbers. And so if you take a 4-point function, if you compute it using the OPE in this channel or in another channel, then the answer should be the same. And so the program of trying to solve a conformal field theory by using this constraint became known as conformal bootstrap. And so here we're about 74 at this point, and unfortunately at the time they didn't make much progress in solving this system. Well, this is a very formidable looking system because it's a system of infinitely many equations, quadratic actually equations for OPE coefficients in infinitely many unknowns. And okay, Polyakov, he managed to solve the system to first order in the epsilon expansion, but that was basically it. And also at around the same time, QCD was discovered. And so both the string theory and the conformal bootstrap, so people lost their interest in these approaches, and it lay dormant for about 10 years. And so in the 80s, string theory was revived, and also in 1983, conformal field theory was put back in focus by BPZ, but in 2 dimensions. And conformal bootstrap again played a prominent role in that revival. But in higher dimensions, it was not until a few years ago that people again started looking at the system and trying to learn something from this conformal bootstrap system. So that's going to be the subject of my talk, these recent developments. So one technical thing which I should start my discussion from is the subject of conformal blocks. So this is one ingredient which is necessary for mastering this OPE associativity constraint. So let me just remind you that in the simplest case, if you take a 4-point function of primary scalar operators, then conformal field theory tells you that it has this form in terms of some function GUV of conformal cross ratios. And by the way, I should add a disclaimer that almost everything that I'm going to say concerns conformal field theory in dimension bigger than 2 and non-supersymmetric one. So this function GUV can be expressed as an infinite sum of terms which are called conformal blocks. So the interpretation of these terms are the contributions of primary operators which appear in the OPE of 2 scalars. So we have infinitely many primary operators, and so this function GOI of UV is a completely fixed function, fixed by conformal symmetry. And the coefficients which multiply these functions are the squares of the OPE coefficients appearing in this expansion. And the unity is the contribution of the unit operator. So we have this expansion. And so these functions are fixed and in principle, but in practice you have to still compute them. And it turns out that there are various choices they can make going about computing these functions. So historically, usually people were analyzing these functions in terms of the so-called z-coordinate. So this is familiar from the 2-dimensional case, but can also be used in dimension bigger than 2. So this z-coordinate appears if you use conformal symmetry by first putting the 4 points in a plane, and then you fix the 3 points to 0, 1, and infinity, and then the z-coordinate in this plane it's this coordinate of the one remaining point. And notice that in dimension bigger than 2, in principle, there is no holomorphicity, but still I can use this coordinate z just as a way of parameterizing conformal blocks, and they're going to be a real analytic function of this variable z in the plane. So smooth real analytic function, and they will have a cut which extends from 1 to infinity. And so the position of this cut is really physically fixed. And so this coordinate z was used to express conformal blocks in a series of papers written by Dolan and Osborne from 2000 to 2011. And so if you are interested, for example, in explicit expressions for conformal blocks, then this is the coordinate you use, just like in 2D. But it turns out that these explicit expressions are available only in a handful of cases, not in all cases of interest. And so you should learn to live with the idea that these conformal blocks are just some complicated special functions, so you should just learn to compute them in a series expansion. And when you organize the series expansions, it turns out that the best expansion parameter is the so-called raw coordinate, which appears very naturally. So instead of fixing the points in the plane like this, you might as well fix them slightly differently. It's the same conformal freedom. Namely, you might fix them symmetrically with respect to the origin. And so the coordinate of the 2 points rho and minus rho, this is this rho coordinate, and it's related by a simple conformal transformation from the z coordinate. It's this function. And the point of this coordinate is that it maps the plane with this cut to the unit disk. And so if you express conformal blocks in terms of this coordinate, then you will obtain expressions which are convergent, actually very rapidly convergent in all the region of interest. So that's why you have to use this coordinate. And so these expressions, they basically look like this. So you have the conformal block evaluated at a given rho is a power series in the powers of the radial direction. And the power here is equal to the dimension of the primary plus the level of the descendant. And the coefficient is the Gegenbauer polynomial of the spin corresponding to the spin of the descendant, which depends on the cosine of this angle theta. And so these Gegenbauer polynomials are less than 1 in the Euclidean region. And these coefficients decay are completely known coefficients. So they can be computed by recursion relations. They are bounded. So so this series is a rapidly convergent series in the whole unit disk. And so the whole structure, actually, this whole structure and the idea of introducing this coordinate is not unlike the idea of Alyosha Zamolodchikov, who introduced the so-called uniformizing Q coordinate to analyze conformal blocks in 2 dimensions. So of course there the story is much more complicated because everything depends on the center of charge. And the 2-dimensional conformal blocks do not satisfy any simple partial differential equations, unlike the d-dimensional blocks which do. But the idea is very similar in spirit. So one thing which I should point out is that these conformal blocks, which if you compute them this way, you see very clearly that they are analytic functions of space-time dimension d. So there's nothing special about integer dimensions from this point of view. And so if you think about defining your theory in terms of this conformal block expansion, then your definition works for any d, integer or fractional. And so if you were ever wondering about whether field theory in 4 minus epsilon dimensions was just a trick, or was it really well defined? Well, this is the non-perturbative definition of conformal field theory in fractional number of dimensions. And so, one nice thing about this conformal block decomposition is that it's a rapidly convergent decomposition, and the way you prove this, you can prove this very carefully and also operationally, meaning that you give an estimate on the error bound, is that you notice that if you take this conformal block decomposition for this function GV, and if you go to the cross channel, so these are the 4 points that you insert them, 4 operator insertion points, and now you increase the radius r to approach this other point, so you tend r to 1, then in this limit you can use the OPE in the cross channel, and this OPE tells you that in this limit this function GUV must behave like 1 over 1 minus r to some power. So it cannot just blow up arbitrarily fast. It has to grow like this. And because of this, it tells you that this, so first of all, it tells you that the nearest singularity of this analytic function is really at r equal 1. It controls you the strength of this leading singularity. And so it not only does it tell you that the series converges for all r less than 1, but it also tells you something about the OPE coefficients which enter into the series. Namely, it tells you that if you construct a spectral density, so if you count each OPE coefficient with this delta function located at the position of the OPE coefficient, then this spectral density, if you average it appropriately, it grows at most as a power law. Well, actually, it grows as a power law. And this is very interesting because if you confront it with the bound for the unweighted spectral density, so if you just count every primary state without weighting it with the OPE coefficient, then from thermodynamics, you know that this sum should grow exponentially in the energy. And so it tells you that in any conformal field theory, the OPE coefficients of states of high energy have to be exponentially suppressed. So this is a general result. Okay. Well, as I discussed, this conformal block decomposition converges, and now we can consider the simplest bootstrap equation, which takes this convergent decomposition and it plugs it into the crossing relation. So the crossing relation just means that I can do the OPE decomposition in 1, 2, 3, 4 channel or 1, 3, 2, 4 channel, and it's the same function GUV which appears, except that I have to interchange U and V, and there is a factor because of the x dependence of the 4-point function. So this is the simplest bootstrap equation, and there's plenty of room to analyze this bootstrap equation because, as I said, the right-hand side of this equation converges everywhere except for this cut, and the left-hand side converges everywhere except for this cut. By the way, notice that here I switched back to the z-coordinate. It's because the crossing looks very simple in terms of the z-coordinate. So the moral is that you should compute these conformal blocks in the rho coordinate, but when you analyze the crossing, you go back to the z-coordinate. And so you see there's plenty of room where both sides converge, and so you can impose this equation anywhere and or at infinitely many points, and this is a completely mathematically well-defined problem. So it's a very, very well-defined problem. By the way, notice, so it's interesting to notice that an analogous problem for the S-matrix bootstrap would not be as mathematically well-defined. Well, I don't have time to discuss this now, but that's an interesting point. And you know, since one advantage for me, the point of these equations being mathematically well defined is not just some point of rigor, but it's just because if some equation is mathematically well defined and still you don't know how to solve it analytically, well, you can still put it on a computer. Well, things which are not mathematically well defined, if you can't solve them, they're useless. Either you solve them or you can't. So, and we don't know, unfortunately, until now, how to solve these equations analytically, although it's a very interesting problem. So what we go, since we are hungry for results, we go by the way of numerical exploration. And there are basically two main directions in this numerical exploration approach. So one direction is trying to identify swampland in the space of CFT data, and another is the study of theories which happen to live or seem to live at the boundary of the swampland. So, this first thing is, so when you chart out the swampland, so the idea here is you're trying to rule out large chunks, you're trying to rule out wholesale large chunks of CFT parameter space which do not actually correspond to any CFT. They do not because there is no solution. So you managed to show that there is no solution to the conformal bootstrap equation. And I'm not going to explain how we actually do it, but the keyword here is linear programming. So that's basically a way to enforce algorithmically this constraint that the squares of the OPE coefficients which enter the bootstrap equation have to be all positive. And actually the practice showed that there are two roads to bootstrap to swampland. So if you take your spectrum and if you try to increase gaps in the spectrum, then invariably you find that your CFT ends up in the swampland. And if you take OPE coefficient, some OPE coefficient, and if you try to increase it again beyond some bound, you find that such a CFT does not exist. And so let me just show you two examples of such studies. So one example concerns, so just take any conformal field theory which has an SON global symmetry, and in that theory consider the OPE. So consider two operators which transform, consider an operator which transform in the fundamental of SON, and take its OP with itself, and in this OP you can have scalars appearing in the representation of the global symmetry, which are singlet and symmetric classes tensor, and they can be, so I'm focusing on the lowest dimension guys, and there could be other guys of higher dimension of any spin. And then it turns out that if you do the analysis of the Bootstrap equation, that the dimensions of these guys, S and T, are not arbitrary. So for, as a function of the dimension of the sigma, there is a certain upper bound such that any CFT is forced to live below these curves. So these thick lines, don't pay attention to these thin lines. So, these lines, you find them numerically, but I also would like to stress that there is a way to prove it analytically that bounds of this sort do exist. So this some recent paper I wrote with my student, something which is called toy bootstrap. So, you know, there is also some analytic playroom. It doesn't give you numerically competitive bounds, but at least it convinces you that these bounds do exist, if you didn't believe. And another example is a bound on the center charge. Well, I'm going to skip that, and I'm going to go to the second part, to the second way of exploring this numerically, which is studying the swampland boundary. So what I mean by that is that if you take, so let's look at this example again. I'm looking at the OP of two scalars, and I'm looking at the first scalar in this OP. And suppose you discover that indeed there is this bound. So here there's no CFTs, and here there are some CFTs. Well, so here there are no solutions to crossing, and geometrically you can think of it as the vector. So this vector corresponds to the contribution of the unit operator, and it has to be balanced by, it has to lie within this cone, which represents the contribution of all the other operators taken with the negative sign. So if this vector is not in the cone, then there is no solution to crossing. And in this region, the vector is inside the cone, and actually it's deeply inside the cone, and so there are many solutions to crossing. But if you go to the boundary, then this vector lies precisely on the boundary of the cone. That's what determines the boundary. And you would think that here there is actually a unique solution to crossing. And you know, this is subject to some caveats, namely, in some generically there's going to be a unique solution to crossing. And so you might ask if there is any interest to go and study these solutions. So do they have any physical meaning? And they would have a physical meaning if by some luck it so happens that some interesting theory lies on the boundary of this swampland space. And actually it turns out that we are lucky. And so if you do the analysis of this gap study in 2 and 3D, so far I showed you 4D plot, but here is a 2D and 3D plot, you see that these plots, they have a feature. They have these corner points. And so you might think that, okay, these corner points, they might have some meaning. And it turns out that they do have a meaning. So this point, actually, if you look at it numerically, it's precisely at the position of the two-dimensional Ising model. So it has dimension 1, 8, 1. And the three-dimensional plot, its position corresponds to the position of the three-dimensional Ising model, this kink. And so, of course, these dimensions for the three-dimensional Ising model are not known precisely. They're known with some error from the RG methods. And but this rectangle, which is the best determination of this dimension, it actually happens to fall right on our curve. And okay, you see that this curve is not precisely a corner point because we're working at we didn't push our methods to high enough precision, but for us it's much easier to increase the precision of these calculations than, say, to compute an extra 8th loop in the epsilon expansion, which is an exponentially growing complexity problem. So this is very suggestive, and actually it turns out that there are other kinks. If you look around, there are other kinks, and for example, this kink that I showed you in 2 and 3, it happens to exist in any dimension between 2 and 4. And actually, if you go close to 4, you discover that the position of the kink is in very good agreement with the epsilon expansion. So if you study the ON model, then again the kink exists, and its position agrees with 1 over n expansion. And so these kinks seem to be rather ubiquitous, and we don't still fully understand why these kinks are there. So we understand that they have something to do empirically with the fact that some operators at these kinks decouple. But why do they decouple? So we are not in 2 dimensions, so there's no ready-made notion of null states. So this remains somewhat of a puzzle, which I hope we will be able to answer. So, but in the meantime, suppose that we take as a working hypothesis that the 3-dimensional Ising model does live at a kink. So what can we do with this? Well, we can determine the full spectrum of the operators which appear in the sigma times sigma OPE. So, and actually, like after 30 or 40 years of work on the Ising model, everything which is known about this OPE boils down to these 5 operators. So this OPE contains infinitely many operators, but people ever bothered to look only at these 5 operators. So it's so the epsilon operator is the first Z2 even scalar which appears in this OPE, and epsilon prime, epsilon W prime are 2 subleading scalars. And this is the stress tensor operator, and this is the operator which is spin 4 current, which is actually not a conserved current in 3 dimensions. So you see it has a small anomalous dimension. That's how it should be in dimensions bigger than 2. So this is all which is known from RG methods, and if we assume that if we assume the kink, then we can determine numerically, at least to begin with, essentially all of them. All of them with their OPE coefficients. So about which nothing is known from RG. Almost nothing is known about RG. And well, by all here I mean not really all, but something like 20, 30 operators you can probably determine. And the reason why you cannot, why it becomes harder in this approach to determine high operators, it's precisely because, as I said, there is this convergence. So the Bootstrap equation is convergent. So it means that the contributions of operators of high dimension are actually exponentially suppressed. So it's becoming exponentially harder and harder to determine those operators. On the other hand, in any quantity of interest, like if you want to predict a correlation function or something like that, the contributions of all those operators that you can determine are really given exponentially small contributions. So if you want to ever compare with the experiment, you don't really need to know much about those operators. Of course, it's possible that if we do this exercise, then we discover some hidden structure of 3D Ising, and then we can make a synthesis and maybe, which will maybe hint at possible ways to analytic solution. But for the moment, I can show you a result of a warm-up study, which was done in 2 dimensions by Elshok and Paulos. So in this plot, what they did is they considered the 2-dimensional CFT, and they only imposed SL2C symmetry to put ourselves in a situation analogous to 3D. And so they fixed the dimensions delta sigma and delta epsilon to the kink, but that's 1, 8, and 1. So these are the exact dimensions. And then you solve Bootstrap with this input, and what you find is that everywhere where there is a red line in this plot, that's where Bootstrap spits out for you a dimension and OPE coefficient of operator which must be present in the OPE. And now you can compare this plot with the blue bands, and the blue bands are centered and have the height corresponding to the exact 2D Ising Virasoro symmetric solution. And you see that the agreement is amazing. And you see that the Bootstrap, the SL2C Bootstrap is able actually to capture the Virasoro structure of the spectrum. It is able to capture these characteristic gaps of 4 units which come from the degenerate degeneracy from the minimality of the two-dimensional Ising model. So, and basically, okay, here you see that some disagreement starts to kick in because these operators already have. You see, this is a log plot in the OPE coefficient size. So these operators have already very small OPE coefficients, and of course they cannot be numerically recovered very precisely. So, so I think this is pretty amazing, and I think that we will be able to do something like that for the three-dimensional Ising model in the near future. Okay, so I'm probably going to finish here, and I'll just going to flash this slide about some other results that I didn't have time to discuss, but which also very much relate to this whole Bootstrap program in higher dimensions. So thank you.
Yeah, thank you for your talk. And are there questions? Yeah.
Well, as I said, no. No, there is. So as I said, there is an analytic understanding of why the bounds exist. So there is an analytic understanding of why you cannot deform, why there is some elasticity limit to the existence of CFTs. There is an analytic understanding of why the contributions of operators of high dimension are exponentially suppressed. And so it means that in any numerical analysis, if you truncate your spectrum at operators of dimension 50, then you're going to be making an error in your calculation of the order e to the minus 50, which is a pretty small number. Well, but the kinks is anyone's guess at this point.
What's special with the boundary that theories want to live there?
As I said, so we do see that at the boundary, the theories which live at the boundary, they have a more minimal spectrum. They have fewer operators than a generic theory which lives in the bulk. So I guess you could try to argue from that the theories which do exist, they are somehow more constrained and they tend to have fewer operators than a generic solution. But it's also a very much open question.
One more question, last.
One of the problems people discuss a lot is where is the end of the conformal window, for example, for QED3. Will your methods be able to shed light on that?
I thought actually a little bit about this problem, but I couldn't find a sufficiently sharp formulation of that problem in terms of the CFT data. So this Bootstrap, it's very good. It proved very good in attacking the problems which have this sort of sharp formulation. Okay, here's the spectrum. Does such a spectrum exist? Here's some OP coefficient. Does such an OP coefficient? Can such an OP coefficient happen? Now that problem about the QED, about the conformal window of QED in 3D, it doesn't seem, so it has some structural properties like the global symmetry group, which also is a starting point of any Bootstrap analysis. But that doesn't seem to be at the moment enough to really start bootstrapping. So there are not enough bootstraps to pull at. So I guess that's a problem for the future.
In principle, you could just look at some operators and see where they hit unitarity bound or something like that.
Yeah, I agree, but that has not been done.
Mm-hmm. Okay.
Yeah, let's thank speaker again. Yeah.